The next topic that we want to do is OSPF. And OSPF, single area OSPF, we got multi-areas, the one that we looked at a little earlier. What we want to look at is OSPF, Open Shortest Path First, which again is the protocol that the CCNA uses. It is a link state protocol developed as an open standard, and it is an open standard used by multi-vendors. Its protocol ID is 89. The thing that we really need to know about it is administrative distance is 110. Where does it fit in to the, are we going to use this protocol? It's between EIGRP and RIP. It is lower than RIP. None of them obviously are going to be lower than the statics when we look at those. Supports equal cost load balancing. Classless subnetting, variable length subnet masks are also going to be supported here. The hierarchy, and the hierarchy we have referred to already with the areas that we shouldn't have more than 50 routers in an area. 50 routers are going to be, to me, is a lot of routers in an area. We connect them together using these things called ABRs, area border routers, and autonomous systems from one to the other. The whole thing here that we have is going to be an autonomous system because we would own all of these, and we had 50 in each one, 150, 140, 200, whatever routers that would be available here. The area border routers connect the areas together. Why areas? 50 routers, going to be a lot of traffic, although it's not going to be broadcast traffic, but it's a lot to keep sorted out, particularly when you start the systems up and they got a lot of exchanging of information going on, so that each router in the area gets all of the information about all of the other devices in the area. So the areas, communicate with each other, or communicate to area border routers, which then send the routing information to other devices in their area about what's going on. Those are going to be represented in the show IP route as IA, inter-area routes, which means they came from someplace else. So we have these within an area. If we have more than one area, and I had always been taught that the first area is area 0, which is going to be the backbone area. All the other ones have to touch area 0. You know, some kind of basic rules. They're all going to communicate with area 0, with the area border routers that go there. If you're going someplace else, down this one down here, the ASBR is the autonomous system border router, which connects two autonomous systems or multiple autonomous systems together. ABRs have one interface in area 0 and another one in a different area. The ASBR's autonomous system border routers connect different autonomous systems. Another organization, for instance, could be connected together. A couple of other things. We have designated routers and backup designated routers. I think that probably the easiest thing to do. Let's go through and look at this and then do the rest of the slides. This is an OSPF, my demo network. I got some serial connections and some connections to switches here. First of all, this, because we've mentioned the term DR, designated router. If I go into this thing and let's just show IP protocols, go through the whole schmear, what you can see here. The outgoing filter list, the incoming filter, the router ID. The router ID is going to be the router ID is going to be the highest loopback interface. If that, well, first of all, we can configure a router ID. We can go in and manually configure a router ID. The next one is going to be the highest loopback interface. If there's no loopback interfaces, it's going to be the highest IP address, the IP address of the highest interface on the network. It uses, you can see this here, these are not subnet masks. These are wildcard masks. And wildcard masks, the easy way to do the wildcard mask, well, a couple of ways to do the wildcard mask. If you take 255.255.25, subtract the subnet mask 255.255.0, 0.0.0.255, that is the wildcard mask. It's also the increment minus 1. When we do that, it's always going to be an odd number. One of the kind of the checks that you can use on yourself is going to be an odd number. The increment, if we have a subnetted, is going to be the increment minus 1, because the increments are going to be even numbers, the 248, 16, 32, 64, 128. And then the area that it's going to be used in. The technical way to look at the wildcard mask is the system checks the zeros to be sure that they match. Is it 192? Yes. Is it 168? Yes. Is it 30? Yes. And the 255s, the ones is, I don't care, it could be anything in this area or in this octet, any number in this octet. Doesn't really matter. We're going to use the same thing. Access control lists use wildcard masks also. So we have the routing for the networks that it is sending information to all of its adjacent neighbors, all of the directly connected neighbors. Its adjacencies. Is it still broken for everybody else? Justin says that its audio is broken. Yay, nay? Back to the recording. So we do these things, the wildcard mask, the other information. These are the networks that are being advertised to area 0, to all of the routers that are in area 0. And in this particular packet tracer file, everything is in area 0. The gateway here, the distance should by now hopefully look a little familiar. 110 is going to be the administrative distance of this thing. The default is 110. So we have these things that are available. The routing information sources, it's 172, 1610.5, 1610.1, 2, and on down the line, the sources that we have for the routing information. A couple of other things that I want to look at. Let's just do some show IP. So IP OSPF, show IP, not IP OSPF, and then what is available. We got border routers, databases, interface, neighbors, virtual links. We don't really have any border routers in this one because we don't have any, we only have one area. But we can look at the interfaces, and this is the interfaces that that are available for OSPF and the flooding that goes on with it. Other things, let's go back to the show IP OSPF information, and I want to do that just so you see the things that are there. Border routers database. The database is the thing that they build, the routers build, and this is what they get. When I look at it, it doesn't make a whole lot of sense to me, but this is what the Dijkstra algorithm uses in order to do the calculation. We have a link count here, the checksum, different information that is available on the links, and the links, remember, are the interfaces that we have for these things. So these are the different interfaces that the Dijkstra algorithm will use in order to calculate the route table. Show IP OSPF. Neighbors is where I want to get to. We saw before we went into the demo in the PowerPoint, we had this DR, designated router, and then we have a BDR, backup designated router. If we have multiple routers in a broadcast case, we have over here, we have this switch, and we have this router, and this router, and this router, and this router that are in this particular broadcast domain. They elect a designated router. The designated router then gets the information. So all of them, and I don't know specifically which one, let's assume that this guy is a designated router. All these guys will send their route updates to the designated router instead of trying to talk to everybody else. The designated router will then send the updates to all of the routers that are necessary, that needed. It's not going to send it back to whoever sent it to. The designated router is elected, and the designated router is going to be the highest router ID, or the highest loopback address, or if that's not available, the highest IP address. So it is an election. This is where the loopbacks can come in handy, although you can just go in and do a router ID command. So we have the DRs and the BDRs that are available on this thing. Oh yeah, I keep forgetting to. So we have these things. We have a DR, a BDR, and then we have a DR other, a druther. This is a device that doesn't have a position, doesn't have an office, not an office holder. The only two offices we have are DRs and BDRs. The designated router and the backup designated router. They use multicast addresses. And I'll get them wrong, but the 6, I think, is when we send information to the DR, and the 5, 224.0.0.6 and 0.0.5 are the addresses that are being used. I tried to, and this gives you an idea of some of the information that goes on to these things. 192.168.1.1. Tried to record a startup, an OSPF startup, and I filtered on OSPF. We have hello packets, and hello packets, hello packet is the way that it finds the other devices. Designated router, hey, we don't know what the designated router is. The backup designated router hadn't been elected yet. We'll go on down in the database. One of the things that it's going to send is a database description. And the database description, when we go in here, is the LLS, the database description sequence number, the data block, 12 bytes, the information that goes in here. Again, these are things that it needs. The source comes from 192.168.21.1, and it's going. This one is going specifically to these are not going to be these are updates for others that are going on. And then we have the descriptions that go on, the request. I didn't get some information. The link state request DB database DB description link state request. If a router doesn't have all of the information that it thinks it needs from a neighbor, then it can ask for an update, request an update. And then we get the update information, the area that we're in, the link state update packet, the LSA type, and these are going to be, we'll look at or briefly look at the link state announcement numbers. But OSPF, what goes on, a lot of traffic goes on, and then the broadcast, if we have acknowledgments here, and then we get the hello packets again. Hello packets go fairly frequently when we do these things, and let's see if we've got a time in here. The hello packet dead interval, the red dead interval is 40. How long is it going to wait before it's going to declare a device not available? There's a hello packet every 10 seconds. Is what they're going to say. These are configurable times, like most. The DRs and the BDRs, multicast addresses. DR, the devices send their updates to the DR in a broadcast area, and then the DR updates everything else. If we look at a point-to-point here, and this one should have two neighbors. If we look at the point-to-point here, we're not going to have a DR and a BDR. Neighbor, we have a two-way, a DR other, a BDR. Actually, well, we got this guy's down here also. That has, and all these eventually go to. So for the one that is in the broadcast domain, it's gonna have a DR and a BDR to do the broadcast there. The others, the serial connections here are just going to be. We don't need an election because in the serial or point-to-point links, we're only going to have two devices, and they're going to update each other. Those things. And, let's go ahead and do. I've just put this one in just to go through a configuration. It doesn't have. Actually, we could put some loopback interfaces on it. And let's do interface LO1. And I don't have any idea what's here. 192.168. Let's do 77.0. 255.255.255.0. I don't know if that one's there or not. Interface LO1. Interface config T INT LO1 T. Does I need to do that? I think. Oh yeah. We create the interface and now we put an IP address on it. You can't do two things at once. 192.168.77, 77.1, 255.255.255.0. And now it likes it. We can give it the no shut command, but these things should be created in the no shut situation. Let's go through how we would do that. Router, OSPF, and then we have to have a process ID, which is only significantly local. It can be any number. It's the way that the operating system keeps track of this particular edition of OSPF. Now when we get here, we can advertise our networks. Network, and I don't know what they are. So one of the things that I like to do, show IP route. I don't want to go out of here. Where did I have the do show IP route? We have these two that we're going to advertise. The 222 is the outgoing interface. It has to be there in order to talk to the other one. Let's do the network 192.168.77.0 and then the wildcard mask 0.0.0.0.0, and then we have to specify the area, and it's in area 0. Nothing happened. Let's go back and let's put in our 222 network, and when that happens, with any luck, we will eventually, or at least we should, routing for networks, routing information sources 77.1, which is where it's getting its information from. I think I know why. So we didn't get a for the 222 we didn't get an adjacency form. I expect that's because show run that this network over here, actually it is doing the let's see if we can ping that guy then. Ping 192.168.222.2, I think was its address. It should be there, round trip 68, and we are all in area 0. Did I mess up the network statement? I can do that. 192.168.222.0. Oh, 0.0.0. I didn't do the 255. So let's fix that. Config T, troubleshooting. The show commands help out a lot. Let's do no network, because it's looking for an address that's 192.168.222.0. No network 192.168.222.0, 0.0.0.0, area 0. I probably could have just, and let's just try it. Let's just put config T or router OSPF, and what did I use for the process ID? 1, and not having a good day spelling, am I? And let's do network 192.168.222.0, and let's do it right this time, 0.0.0.0.255, and then area 0. Too many zeros in there. So now with that one, now we get an adjacency. And when we do that, we should now be getting show IP route, spell again. We're getting all of the information from all of the other routers. And if I do a show IP OSPF neighbor, the only neighbor that I have that's directly connected is this guy. It's in the same domain, and it's going to be the designated router, the DR. I'm going to update it, and it's going to send me the information. That means that I'm going to be the backup designated router, because on this we need a DR and a BDR when we have these two. Whichever one is not the DR is going to be the BDR. So we have this around the world now back to the designated router. Messages are sent to the fully converged network. It's going to reduce traffic. Fully converged network when we have changes. We have the hello messages when we are converging, the ones that you saw in Wireshark. That goes on and on and on and on and on. Selected on a per segment based on the highest priority. And the default priority for everything is 1. Priorities can be changed. If all the priorities are the same, then the highest router ID, which we can configure in the router OSPF command. If I wanted to do that, we'll go back to this one that I had. Let's go back to the one that I just added to do that. So we can config T, and we go back into the router OSPFJune, back into the process, and then we do a router ID, and then it looks like an IP address. Let's do 199.199.199.1 just to do that. Then it says that in order for this to take effect that I need to use the clear or we can reload it. So let's go in here and clear, exit, clear IP, OSPF, SPF. So let's go back into the router. Let's try it there. It's not, doesn't like it. So Packet Tracer doesn't like this command for me. Clear, doesn't like the clear. And then the tab should have given me a hint there, right? The tab didn't work. OSPF process. Do I want to reset all those? And I'll say yes, the default is no for that. It's going to reload things. And now the DR may actually have changed on this thing. Show IP OSPF neighbor. Now we're connected to the BDR. Since I set the router ID to a pretty high number, when I restarted all the processes, did the exchange of link state announcements, the hello packet exchange, said, oh, you're got a higher than everything else, so we'll make you the DR. So you can dictate the DR and the BDR by changing the priorities of these things. The DR listens on multicast 224.0.0.6, and I think I did get it right, for updates, and the other routers listen on 224.0.0.5. So the updates are sent to the multicast address, the .6 address, and it tells the other routers what the changes are on the .5 address when we have those things. The BDR takes over if the DR, the designated router, goes down, and all the others are DR others, which we saw in the show IP OS. Dynamically discovers neighbors to form relationships. You saw those happen. The intervals, 10 seconds for the broadcast segments, and we saw that in the link state announcement in Wireshark that the interval was 10 seconds. This is in the broadcast domain, and that was because it was looking to see if we could see it going to the DR and the BDR. I never actually got anything to do that. 30 seconds on the non-broadcast segments, the serial connections, to be sure that, you know, we're still there. You still there? And that's all the hello packet is. Are you still there? Are you still there? You know, kind of like the kids. Are we there yet? Are we there yet? Are we there yet? The dead timer, 4 times the hello timer, and that's what we saw was 40 seconds. The dead timer is, I don't think that router is still working. I don't think it's not talking to me, at least. Maybe the process got interrupted. Maybe the interface went down. Maybe somebody shut down the router. The process ID, when I did router OSPF and then a number, that's the process ID. Identifies the OSPF running on the router. It's for the router to keep track of that process, and it's only locally significant. Each of the routers can have a different process ID. Neighbor adjacents, the hello and the dead intervals have to match in order for an adjacency to happen. So the timers have to match. The area ID's got to be the same, and if we configure authentication, that's got to be the same. The link state advertisements, communications between the routers to update the routing topologies. For IPv4, the RFC 1131, version 1 was in 1131, but it was never implemented. OSPFV2 is the one that we're using right now by IETF Link State Protocol, and it supports IPv4 routing. Neighbors is discovered. The routers compare the information in the hello packet and determines whether the routers have compatible configurations. The timers have to match. They got to be in the same area, basically, is what we have to have. And then the password, if we have a password. Synchronize the databases through the exchange of link state announcements, and they'll try to form an adjacency. We'll flood the link state announcements out of every OSPF enabled interface, and that's where those become important. They get to be OSPF enabled when we put their network in the network statement in OSPF. So you do, in order to enable it, you have to advertise the network that the interface ID IP address is associated with. And the show IP routes that I did there, that's I think an easy way. I don't have to remember them. It shows me which ones are there, which ones are on this device, and the activate on the other ones to be able to communicate with the neighbors are the ones that are going to be C's and L's. Well, the C's and L's, all of them are. The C's and L's are the ones that we're going to advertise. We have those. The area, a logical division of routers, we've looked at that a little bit. Logical division of an autonomous system so that we don't overload a particular group of routers with traffic, exchange of traffic to get the information that it needs in order to form the tables. Smaller routing tables reduces the link state announcements into flooding, and that's when we're starting up. More efficient use of resources, and route summarization is more effective. And this is another one in the areas that you may want to, or you should consider hierarchical IP addressing, so that we don't have to send so many routes. We can use a hierarchical arrangement in order to do that. The area ID is assigned to the interfaces within the defined area, and I think that we saw that in the Wireshark, that the area was specified in the announcement. The area ID is a 32-bit value. It looks like an when we do that, just like the router ID looks like an IPv4 address, when it really is a 32-bit number. It can be entered into area ID. 32-bit can be entered it can be entered as a number or a dotted decimal notation, such as 10.12.13.11. Area 0 again's got to be our first area, and I think when we looked at it, it was everything was 0.0.0.0. Before the adjacencies can form, the things that have to match over here, the area ID, the subnet has, or they're not going to be talking to each other. Hello and dead intervals, authentication, stub area flag, and this is something, stub areas, we're going to have a couple of things to talk about stub areas. That's beyond CCNA. A stub area, basically an end network. And then there has to be a unique router ID. We cannot have devices that have the same router ID. And for, that kind of makes sense. Everything has to have a unique ID. Adjacency is a relationship between neighboring routers that we're going to use for these things. The requirements got to be in the same area, same authentication, same subnet, same hello and dead intervals, same stub flags. How do you find the hello and the dead intervals? Think that, let's see if we can see that. That was in maybe the show IP protocols. The reason I do these things, these are kind of some of the things that they used to figure out. Path, stub area, this is the maximum path. This is the equal path cost sharing, equal cost sharing interface. That's broadcast type or not. Yeah, that's where it is. The timer intervals configured. The hello timer is 10 seconds and the dead timer is 40 seconds. Retransmit is going to be in 5 seconds. So we can look at the IP OSPF interface to find the hello and the dead timers. These are things that have to match for an adjacency. And notice we got a cost here too. The cost is 1 across these things. Router ID, a number of information. These are things that, poke around and look at these things as you're doing labs just to see what's available where, and then why is that particular thing important. Not all neighbors will establish an adjacency. The adjacencies established using the database description packets, link state request packets, and the link state update packets in OS. On the point-to-point and point-to-multi-point links automatically establish adjacencies. We didn't have the problem. We don't have to have the DR and the BDR. We looked at those when we do that. The non-broadcast multi-access frame relay, yeah, that can be an issue. Frame relay is an old protocol that's really not used anymore. I think that the only thing that we need to be concerned with right now are the broadcast area and the point-to-point. The Ethernet non-broadcast multi-access may have to be configured manually when we do these things. What we have in here, typically the area here is 0. All of this information would be in a frame relay. We would have single devices on these. It's a non-broadcast multi-access is what we're talking about here. So it's not a switch, but we have multiple accesses on these things that can be configured. It is kind of an unusual circumstance and wouldn't, I don't think, happen in the enterprise. And this certification is kind of focused on the enterprise management of these things. The router ID is a 32-bit number, uniquely identifies the router in the OSPF database so that we know which devices, which information came from. We can do it manually, which we did with the router ID command in the router OSPF area, the router configuration. The highest IP address on the loopback address will be the next one. If there's no loopback address, is the highest IP address that's on the router. And those are used in the election of the DR and the BDR. The one with the highest router ID is the one that's going to win the election for the DR, and the next highest will win the election for the BDR. The link state announcements, and these are just, we saw kind of what one looks like or in the packet tracer, and those scans, if you ever want to look at them, are in the share folder. The routers are in the same area. OSPF0 type 1 is going to be used for them to share information. Type 2, sent by the designated router. Summary area routes sent by the designated router for these things. A type 3, routes from other areas generated by the area border router, that it would use the area border router between the areas. Type 4, area system border router. I used to try to memorize these things, but I was never asked what they were, just that we have link state announcements to share the information. That type 5, routes from other protocols. This would be a pretty complex OSPF configuration. We have the area backbone link state announcements 1, 2, 3, 4, and 5 are going to be in here. An area border router sends link state announcements 3 in here within the area 1, 2, 3, 4, and 5, within all the areas here 1, 2, 3, 4, and 5. These over here are specified as stub areas, and again, you just look at it and say, oh yeah, that's really cool, because you don't really need to know about these yet. They are there. These are different configurations, different properties that can happen with these things. But a stub area, link state announcements 1, 2, and 3. Then we have a total stubby area, total stub 1 and 2, and then an NSSA not so stubby area 1, 2, 3, 4, and 7, and then a total not so stubby area. So it goes on and on and on. If you go into CCNP, you'll need to know about the not so stubby areas, the total stubby areas, and the stub and the total stubs. What we need to know about, we're concerned about the single area 0 configuration. The DRs and the DRs, and we've already looked at this in the packet tracer, the IP OSPF neighbor, the DR and the BDR, central point for the OSPF information exchange, multiple routers in the same multi-access broadcast domain. Everything's connected to a switch. Essentially, is what they are. The non-DR and the non-BDR routers exchange information only with the DR and the BDR, not all the other ones. This configuration was designed to minimize the amount of traffic that went on in those areas. Reduces the number of updates that have to be sent, and the priority is used to elect the DR and the BDR. And if the priority is the same, the highest router ID. Summary slide here, and I'm going to leave this one, I think, for you to look at. We got a couple of other things to do. Actually, probably about 2 or 3 more slides before we take a break and then work on the labs. But the protocols OSPF RIP-V1 and RIP-V2, the classless VLSM auto summarization, all of the properties of the different protocols, not all the properties, but some pretty significant properties. And then there are a couple of labs. We're going to consolidate them here after we talk about a little bit more about OSPF, the multi-area, which is interesting to know about. You may get into a situation that you need to configure multi-areas. It's not anything that's really all that complex to do, except to know that the first area, and it's easier to say, hey, the first area is going to be area 0. Then we can create other areas, area 1. When we want these guys to communicate, we got to stick this other router in the middle here and put 2 interfaces on it, 1 interface in each of the areas, so that it becomes the area border router. It's the relay of the routing information from one area to the other area. So with a backbone area, 1 or more routers will become the area border routers, allow connections to both backbone areas and at least one other area in here. The area border router, we're going to have a separate link state database for each of the areas that it's connected to. Defines OSPF-V2, defines one other router type, the autonomous system border router, and I think we talked about it a little bit earlier. It goes outside of our area. Where would it be? Maybe going to your ISP if you wanted to. Probably what you're going to use going to your ISP is a passive interface. Connect an OSPF area to another autonomous system, some other management domain or manage. IPv6 is kind of a little bit different. We'll look at these and I want to show it. Protocol supports the following features over those OSPF v2, OSPF v3 routing for IPv6, support for the IPv6 routing prefixes. The link state announcements need to be expressed in prefix and prefix length instead of address and mask. The router ID, and you do have to configure a router ID separately for OSPF for IPv6 because it doesn't have that 32-bit number that it can use on the interfaces, and it's still going to be a 32-bit number. Looks just like the one that I configure in the same place with the one that we looked at in the demo. We'll use the link local IPv6 address for the neighbor discovery. IPv6 is going to, or IPv6 is going to use the link local address, the FE80 address for all local communications. Version 3 uses IPsec for security authentication headers or ESP encapsulation security payload. It's going to be, what this is saying, is going to be more secure v3. New link state announcements are the same as IPv4, and the type 8 is a link local link state announcement, and then the type 9 is going to be an intra-area. Another summary slide. What are the differences? Version 4, version 6. They're both multicast. Multicast for all routers. The IP address 224.0.0.5. FF02:5. The thing that they did for us was kept the same. 224.0.0.6. FF02:6. Recall from IPv6, FF02 is the local multicast address that we use. Authentication, version 2, plain text or MD5, IPv6 authentication for version 2. IPv4, IP unicast routing, IPv4 is enabled by default. We have to give the router the IPv6 unicast routing command in order for it to route. The header is the 16 bytes. The version 3 is actually smaller, more link state announcements. The interface ID, the IPv4 address, and then again in version 3 for IPv6 we're going to use the link local address. This is one of the differences. OSPFV2, we had to, if we had multiple areas, we had to have an interface in each area, and an interface could only be in one area. In version 3, we can have an interface in multiple areas, which kind of, I guess, makes it a little bit simpler for these things. The configuration, and I think for the configuration I want to look at one. I won't make you suffer through doing one. See if I can get one open here. OSPF IPv6. Now this one's a multi-area. It doesn't make any difference about that. What we want to look at is the configuration requirements. It said it's a little bit different. We got the adjacencies forming over already. The neighbor, then this is going to be the router ID for the neighbor that we would have for this thing. We do a show run here. The first thing we have to do is IPv6 unicast routing. We have to turn routing on. On the interfaces, we have the IP address here, and then we do IPv6 OSPF1 area 1. We assign the protocol and the process ID, and we have to start it down here, we will in a second, and the area is specified on the interface itself. There's not a network statement. Router OSPF1, IPv6 router OSPF1. We started the interface, we started the process, so we have to have a separate announcement. Since this one is dual stack, you can see it has IPv4 as well as IPv6 addresses. OSPF will take the network ID as one of those. Realistically, we should go in here and configure one. Let's go ahead and do that. Config T router OS. Let's see, router. I think it's IPv6 OS. Router OSPF IPv6. We the only ones it gives me in it. Now I got to go back and figure out what I'm messing up on that. But anyhow, we should have in here IPv6 router OSPF. Should be IPv6. IPv6. Yep. And I guess I spelled IPv6 wrong. Router. RPS OPF. Router. OSPF, and then the process ID, and it was 1, right? Because we don't want to configure the wrong one. And now that we got in there, we can do router ID, and let's do the 199.199.199. Same as we did. And it's the same thing. End here, although this one really shouldn't make any difference because we don't have anything elected in this case. Clear IPv6 OSPF process, and we'll do a yes, and it will do that. The detach and it'll come back. The neighbor is down, and now we show, and now we're done. Show IPv6 OSPF neighbors. You have to remember, and I mess that up. Since it's a serial, we just have the full. We don't have the DR and the BDR, which we would still have. For these things, but you do have to have, and I did all that to try to emphasize that you got to have a router ID. This one happened to pick up, because it's a dual stack, it has both version 4 and version 6 addresses on it, happened to pick up the version 4 addresses, the IPv4 addresses as the router ID. But first we turn on the IPv6 unicast routing, enable the process IPv6 router OSPF, enable Cisco Express forwarding on it, and then give it a router ID. Once that happens, we advertise the networks, and we advertise the networks on those things. Advertise the network, interface loop back, IPv6 OSPF, the process ID, and then the area. are configurations that are going to be on the interfaces themselves, and that's what I wanted to show on that one, and hopefully that made sense. Configure the neighbor routers so that they're going to talk to each other. Check for adjacency, show the IPv6 route OSPF, show IPv6 OSPF neighbor. Same commands except we have to specify IPv6. So we are now up